All right, so before we work this problem, which has a few different scenarios to rank, okay? Day one with the original rotation, we wrote out old equations and compared the new. Let's do that now. And so we're getting into energy. And so remember there was that work energy theorem. Work was a force times displacement. And so now, so you've got your linear translational. Translational is another way of talking about linear motion. And then we've got the rotational. So paper people, hopefully you have some room to squeeze it in maybe above that picture. I am going to do some force diagrams, so just FYI. And so our old equation for linear objects, FD cosine theta, yes, but that parallel force with distance. We had work energy theorem, net work equals a change in kinetic. What was kinetic energy? 1/2 mv squared. We had potential. Now it turns out potential is going to remain mgh. We'll still be using mgh. Your rotation is different than the height above your lowest point. Rotational quantities, well, we still have work and it doesn't get a new variable. But instead of a force times distance, it's really about the torque times an angular displacement. Okay. Net work is still going to be a change in kinetic energy. So that part is actually the same, but the types of kinetic energy, now that box that slides down the ramp and only has translational, 1/2 mv squared. Now we put a round object on the ramp. You can still have linear motion, but now we have rotational. And so you'll see me start adding another subscript to kinetic energy. There's translational kinetic energy, still going to have it. You still have linear motion as you move down a ramp. But if you're also rotating, well, sometimes it takes more energy to rotate different shapes compared to others. So here we go, 1/2 I omega squared. So similar to what we've done before in terms of F equals ma, inertia is that mass term, but shape matters. And then omega is that angular velocity quantity, and it kind of fits the same format. Oh, yeah. So capital W work. You may write lowercase w, but it's the Greek symbol omega for angular velocity. I'll be honest, a lot of physics teachers, when you type physics, they'll write a lowercase w, right? Because you're looking at context of the equation. But I would try to omega it, rounded lowercase w there. Everybody good? Okay. And real quick, while we're here making our list, momentum will probably start next class. Let's get some momentum equations. So back in the day when we just had objects going straight, we had momentum, P equals mv, right? And we talked about changes in momentum were due to impulse, right? And so we had impulse, J, and just so we don't think it's joule, impulse equals a change in momentum, which could be m delta v, most commonly. Well, now with rotational quantities, okay, and so here we're getting into that figure skater, arms in, arms out, okay, that's really an application of conservation of angular momentum. But now we have, watch it, capital L, not length. That's the variable for angular momentum. And I believe it's labeled that way identically on the formula chart, equals I omega. That mass substitute basically, and then the velocity substitute. And so a change in angular momentum is commonly change in angular velocity, but your inertia could change as well, okay? Or it could be a change in inertia. I hate to put a delta with both of them, but Changes in angular momentum happen because of an impulse. I don't think we have a impulse variable for angular momentum. Yeah, it's just change in L. Okay. Oh, and the other part of our linear equation for change in momentum, we also said it was a force times change in time. Now it's not just about the force, but it's where that force acts on it. And so a change in angular momentum is a torque times time. You're still exerting a force to make changes, but that lever arm reference, where you exert that force matters. Is this making sense a little bit, the comparison? Most of them, I think, are. So of the new ones, L equals I omega is, and so I'll just put, FC for formula chart. Rotational kinetic energy is on the formula chart. What else? The torque times time is. I guess you're expected to know that impulse would be I times delta omega, or if I is changing, you got to consider that. The work one is not, okay? But hopefully looking at the comparison, left side, right side helps. And I can think of another derived one that we'll get to. It's not on the formula chart, it's more of a derived one. So we'll hit at least one more angular momentum later, okay? And so there's our comparison. Now focusing on energy, we've got a uniform cylinder. The K value is 1/2, so the inertia would be 1/2 mr squared. It's allowed to move down an incline, allowed to move. Are we pushing it? No, we're not pushing it. It's just going to be released from rest. So just like he did in the videos, right? And again, I could demonstrate, I don't have a good ramp. Okay, not a sturdy ramp. They bow in the middle. And so you actually have a curvature, and that would be different. But they're going to start from rest. We've got 3 scenarios to compare. And so we see a picture here. So it starts from rest. It has no initial linear velocity and no rotation. Well, you can see in the picture, it's just saying on the way down, it's going to accelerate and angularly accelerate. And so you're going to end up with a final velocity, translational, linear velocity, and you're going to end up with rotation. Who's causing the rotation? To answer that, we need a force diagram. And so this is just one object going down 3 different surfaces. Let's see if it's gravity or not. And so your diagram well, I guess it does depend on the scenario. So let's draw the 3 scenarios here. So we've got a frictionless incline. We've got an incline with some friction, but not enough to prevent slipping. In other words, we're going to roll with slipping. Hint, hint. We might be skidding. We might be rotating. There's slipping involved. Here's my slipping visual. Rubbing my hands together. Why do we do this? There's heat loss, okay? And so note to self, the big thing, by the way, we don't do nitty-gritty math with this one. It's more complicated, okay? The math we do is either going to be frictionless or non-slip, but here, note to self, you have heat loss, okay? When it's with friction, with slipping, it means that friction is not gripping to rotate. And then, of course, scenario C, you have sufficient friction. Now we have a good amount of friction to prevent slipping so that you roll without slipping. And right there, that phrase allows us to use what equations? Well, yes, rotation, but that V equals omega R, A equals alpha R, and then the distance one would be delta X, linear distance, equates to an angular displacement times R. Now today we'll mainly be with the V one, the velocity, because we're going to look at kinetic energy. And it talks about preventing slipping. And so instead of kinetic, like we have above, kinetic friction is the shearing, the slipping friction. If we have gripping here, it's going to be what kind of friction? Static. So those are the things that as you read the different scenarios to keep in mind. Well, technically, these have different force diagrams, okay? Overall, it's similar, but the friction is varying, right? And so for A, scenario A, no friction, mu is 0. We've got a ball on a ramp, and we're not drawing the velocities, which are changing, right? We're just drawing the forces acting on it after we let go. And so what forces are acting on this object? We got gravity from the center of mass, whether it's hollow or not. We got the gravitational force. Normal force is drawn from the point of contact, the surface, and it's maybe touching at that one point. It's symmetrical. So we've got normal force. Yeah, this one's, there's no friction. So what other forces are acting on it? None. So who's going to cause scenario A to rotate? Well, to consider that, we need lever arms, we need a fulcrum, we need a hinge axis of rotation. For this round object going down the hill or the ramp, where's the axis of rotation? It's at the center. And so if we also kind of designate with the triangle, okay, it's also at the center of mass. Well, how much torque, how much lever arm does gravity have? 0. What about normal force? 0. There's no other forces, no other lever arms, no other torques. What's going to be true about object A? No rotation, okay? Or look at it this, there's no torque, net torque on the object to have an angular acceleration. There's no changes to whatever rotation you have. And if you start with none, you end with none, right? And so scenario A, note to self, 0 net torque, angular acceleration would be 0. And so your changes to omega would be 0. So the picture is just kind of overall, right? But there is no alpha, there is no omega, because we started with no rotation, we end with no rotation in scenario A. It's just like a box. Okay. Everybody good there? All right. Actually, I'm going to go ahead. I know it's going to be all over the place, but let's go on and write an energy statement for this A scenario. And so it starts at the height, a highest point. So what kind of energy does it have in the beginning? Potential energy. So for A, so this is still A, we begin with mgh, and it's at rest, and so there's no form of kinetic in the beginning, equals, now where's all that energy gonna go? Kinetic. What kind? Well, yes, final, but is it gonna be the linear translational kinetic, or is it gonna be the new rotational kinetic energy? Just linear, so it's the good old 1/2 mv squared. And that would be a V final. Now, is there anything more to it? Well, we already said there's no rotation at all. Is there going to be any heat loss? No, because it's frictionless. There's not even kinetic friction. So that's it, right? Now, while we're here later, we're going to need a final velocity for a ranking. Can we go in and solve for the final velocity of A's scenario? What do you notice? M's cancel out, multiply both sides by 2, square root should feel familiar. And so square root of 2gh, just like a box. So why doesn't this one rotate? Well, there's no friction at all. There's no grip to rotate, okay? Everybody good with scenario A? Let's try scenario B. Now I wish I'd put them all in the same color. So ignore any color coordination. I apologize. I don't know. Now I want to record again and color coordinate better. Anyway, B, B has the heat loss, right? So what would the diagram look like for B? Well, we still have the same center of mass, same hinge, axis of rotation. We still have the same gravitation, right? So Fg down, normal force, perpendicular to the surface. Neither one of them is going to provide any torque still. Okay. Now we have friction. It's going to be slipping on the surface. We're going to have that shearing action, just like we did with a box. What direction is friction going to act on this object? It'll be up the ramp. Okay. And I'm not going to put a subscript with it because here, sometimes we'll be slipping, sometimes we'll be rotating. And when you have moments of slipping, it's going to act just like a box, right? When you have moments of gripping, notice that this force has a lever arm equal to the radius, right? So when you have moments of grip, then it's going to have what kind of torque? What direction of torque? You wrap around, it would be clockwise. So the torque due to friction, and I'm going to just put a wavy symbol because it's not a constant. It says we don't have enough to totally prevent slipping. And so that torque of friction is going to be in the clockwise direction. That's going to be like forward. So you can call that the positive direction here. Okay. And so we will have an alpha, we will have changes in omega. It's just not a constant, right? Good on that one? No other forces. Now, what would our energy statement read? Well, we would have mgh, actually identical to before. If these are all the same objects, same mass, just on 3 different surfaces, but they're all the same height, they all have identical starting energy. Now, though, watch this. We're going to have some heat loss. Now, in here, we don't get into, Q or MCAT. That's not in AP1. So our heat loss is going to be work done by friction. And so this is our heat loss. Now, you can show it as a subtraction on the left-hand side, or you can say all the energy we start with gets turned into these types of energies, one of them being the heat loss, okay? Plus, isn't it still gonna have 1/2 mv final squared? But hopefully you realize that, well, when heat loss takes away some of that energy, we're not gonna be going as fast. But we also have some rotation. And so can I squeeze it in here? Plus 1/2 I omega squared. And you have to keep it in this form because it's not non-slip. Again, this is just the concept of the types of energies it has, okay? We're not going to be doing the math with this one. It's not consistent. You're not consistently gripping. You're not consistently slipping, okay? You have different time periods for each. And so A is relative to what we would be expected. C is going to be definitely required. That's the big one coming up with C. B is that somewhere in between. And so what would C look like? So I'm going to use the space down below. We still have that cylinder, whatever it is, starting from rest in both directions, linear and rotational. What forces are acting on that object? We still got gravity, same as before. Normal, same as before. Are they doing torque? No, because our axis of rotation is in that same center of mass location. So torque normal, still 0. Torque gravity, still 0. But now we have the non-slip condition. In other words, no shearing, no slipping, no heat loss. And so that's one of the big differences here. no heat loss. And so we still have friction, but its job now is not to slip, it's to prevent slipping. It's going to be gripping. And so here, what direction are we going to draw the force of friction? We know we're going to rotate clockwise as you go down the ramp, right? Hopefully you know, and it's not gravity, it's not normal causing that rotation. Who's causing that rotation? Friction. And so what direction is friction to give us that direction of rotation? It's going to be up the ramp. And you're like, duh, get ready on the next page. Friction's going to be a little different. And so here I am going to label it with the force of friction, S for static. And just as a reminder, this is our gripping, okay? This is that special case that AP likes that you hopefully do a whole lot of. And so there's no heat loss. And so let's go ahead and write our energy statement and no other forces, okay? No other forces. Now let's write our energy statement. Same MGH. It's just now we have a better grippier ramp. And so no heat loss. I'm not going to write work done by friction. And we're still going to translate, meaning we still have linear kinetic energy. And now we're going to rotate. Okay. Now again, this V final is different than above. Okay. It's different than above. Let's take a look at I omega squared and do some substitution, because a reminder, we are non-slip. So we get to plug in something for omega, okay? And so I'm going to go ahead and plug in our KMR squared for the inertia. I know they gave us the shape constant, but just pretend they didn't. Keep it very, I don't want you to confuse the 1/2 in the kinetic energy equation with the 1/2 shape constant on this problem. Now, what can we plug in for omega squared? Well, if omega is equal to v linear velocity over radius, and if I want to square omega, what do I have to do to the right-hand side? Square it all. And so I'm going to plug in linear velocity squared over r squared. And what do we notice happens? R squared, it's the same disk. We're talking about the same tangent point with the same radius as the disk. R squared cancels. So the demo yesterday, or last class, he said, I got a teeny tiny radius and I got a really big radius. Why did they tie? Why did no winner happen? Radius cancels. And so what's left? And so we get 1/2 K M V squared plus, and that's a final tangent velocity of the disk. Isn't that similar to the original kinetic energy? Yeah, can't we factor out 1/2 mv final squared? Okay, and so to factor that out, we get mgh equals 1/2 mv final squared times 1 would remain plus k. And we could write one more statement. What also happens? Mass cancels. Okay. Now, I'm not going to necessarily solve for V final necessarily, but here that non-slip condition has a direct connection between translational and rotational. And so the one going the fastest, I guess let's solve for it. Let's solve for it. V final would equal, I still got to multiply both sides by 2, so 2gh. And before I take the square root, we need to divide by that expression 1 plus k, and then square root. So if you compare that to what we had for part A, where it was just square root of 2gh, well, let's look at these shape constant. He said hollow always loses. Hollow shape constant is 1. A cylinder is 1/2. So the bigger the shape constant, the what? The smaller the final speed in the linear direction. And if you think about winners of races, you want the quickest time, right? You want to be going the fastest. And so hollow always loses. Hollow has a large K, always loses. Good deal? And the reason is, if you were to go back to the original energy statement, it has more inertia and it takes more to rotate it. So remember that 1/2 I omega squared. Hollow, higher shape constant, more inertia. It puts more of that potential energy into the rotational bucket, if you will, leaving less energy for the translational kinetic. Does that make sense? Okay. We got force diagrams for all three. We got energy statements for all three. I believe we should be able to do some rankings. Who's going to have the greatest final velocity at the bottom? Well, who puts more energy into that 1/2 mv squared term? In other words, who doesn't put energy in other buckets? The frictionless, A. So A is going to be greater than, who would come next? B? Because it's more complicated. Yeah, we're not going to solve for the B one because we don't know how much work of friction is done. It's variable. It's not consistent. You're losing heat and you have probably less torque, right? And so B is next. It's somewhere in between, okay? Because you do have moments of grip. And so who's going to have the smallest? Well, it's the one putting the most into rotation. And so we've got C there at the end. B on a lot of these rankings is going to be in between. What about the final angular velocity? Who's rotating the most? C. Who's rotating the least? A. Who's in between? B. Similar to those two rankings, translational kinetic. Who has the most translational kinetic? Well, who doesn't rotate at all? Who rotates the most? Who's in between? So these are going to be the same rankings. 4 is just like 2, because to answer the angular velocity, you need to know who has the most rotational. And that would be C, and then B, and then A. Okay. Now switch gears just a little bit. Who has the most total energy at the bottom? They all start with the same. A and C are equal. Why is B least? Heat loss. And it totally leaves, right? You don't get it back. Now for acceleration and angular acceleration, yes, we can now go to kinematics, or we just kind of go back to forces and torque. So this is kind of old. And so who's going to have the greatest linear acceleration? Well, that would be the forces bringing us down. And so if we think about the forces, A, the net force was your mg sine theta. Y'all, ramps are coming back. Theta's there. It is gravity bringing it down the ramp, but it's not all a gravity. It's a component. Y'all remember parallel? Yep. And so mg parallel is that mg sine theta, right? For B, it's also mg sine theta, bringing it down the ramp. And we'll say down forward is positive. But then we've got this kinetic friction. And for C, MA, mg sine theta, all that part's the same. But now we have static friction. And so if you remember, static friction has a higher coefficient, your normal force, is all the same on all these. It would be the mg cosine theta. And so it's really based on that coefficient. So knowing that mu s is greater than mu k, who's going to accelerate the most? A. Who's going to have the lowest linear acceleration? C, because you're going to subtract a bigger value of force, of friction. And B is somewhere in between. And if you thought about kinematics, they all travel the same distance down. You know something about the velocities. And so you could solve for, they all start from linear rest. You could kind of solve for acceleration with kinematics there. Angular acceleration, well, this is net torque. And so net torque, hold on. Net torque, I alpha, who has torque on A? The one just sliding down? No one. So angular acceleration is literally 0 on A. B, net torque, same I alpha, same inertia. Who's rotating this B scenario? Sometimes it's a friction. Okay, so we do have a frictional force times a lever arm, which would be the radius, right? But we'll have some alpha, okay? It's just not consistent. It's not 100% of the time there. And then C, sorry, I'm having to squeeze it in. Same I alpha, but this time we have force of friction that's consistently rotating it. It's a consistent grip, so it would be the most. Okay. And so there you see the ranking. C is going to be greater than B, greater than A. And again, you can think about angular kinematics, you know, something about their angular velocities. The displacement's going to be this, angular displacement would be the same. And so, good on those? Okay. 8 is going to have us focus just on that non-slip because that's what most of the time you'll be doing. If the cylinder were replaced with the following, what would happen to the linear velocity and the angular velocity at the bottom? So we're thinking just scenario C. Okay, so only C. Non-slip. And so I'm going to rewrite not the whole thing, but that energy statement, just the original, so we can kind of look at it. And so we've got that mgh equals 1/2 mv final squared at the bottom, plus that 1/2 I omega final at the bottom. And don't forget I is that kmr squared, and omega f, if needed, you can substitute that v squared over r squared. Okay, so no heat loss. We've got that nice gripping friction. And so each of these has two answers, and I'm mainly doing this so I don't forget. In the past, I've got so excited I forgot one. And so each of these, we need to figure out what happens to the linear and the angular. And it's just an increase, decrease, stay the same type. So what if we use a cylinder with more mass? Nothing happens, right? Mass cancels when you break it all down. And so same. Both of them, right? Same. And you saw that demonstrated in the video. What about a cylinder with a larger radius? So if I was to plug everything in and solve for V final, what would we get? Radius cancels, so same. However, omega, when you keep it in omega terms, you can actually use the non-slip equation that omega equals V over R. If I have a larger radius, but the same numerator, what kind of angular velocity are we going to get? Less, so smaller. So decrease, smaller. And then here's kind of the, the aha moment of the video. What if we use a ring instead of a solid cylinder? Same mass, same radius. Now it just has a larger shape constant, okay? Okay, and so, yeah, you go back up to where we solved. We had already come to that conclusion. We said the larger shape constant gave us a smaller linear. And so we know that this is going to decrease. And omega does depend on that linear velocity, same radius. And so kind of using that same equation, but now our denominator's the same, but we have a smaller linear speed. So what are we going to get for angular velocity speed? Smaller, it's going to decrease as well. Direct relationship with the same radius. Good deal. And again, that's why hollow always loses, because it's not translating as much. Good on that page. Questions on the new energy? 1/2 I omega squared. Plug in your non-slip most times. Well, let's look at page 2. And let me, get a preview timing. Yeah, I think so. 3, 4. Oh, we got to get to pole A. Okay, so maybe we get this one started and then y'all can try these rankings, okay? It's similar in format as in the front. So the feel of how to solve this is going to be the same. But now what is our ball doing? We're going to roll it up a ramp. And so it doesn't magically start rolling up a ramp. You actually have to give it a push, an initial push with an initial spin. So we're going to have an initial velocity, linear and angular. And so let's draw a force diagram. Let's get some setups going. And then I'll have y'all try this if we have time later. There's 2 more pages with energy. I want to get as much as we can, okay? Okay, so same type of scenarios, just in symbol form. And so scenario A is going to be our frictionless. Okay, B has some friction. And I'll go on and cut to the chase. This is going to be the one that has heat loss. Okay, and then C is going to be the gripping friction. Sufficient. And so we're going to have non-slip. And that's going to be the most important one, okay, for this unit, for rotation. A is going to be like a box, right? Good old box, good old forces kinematics. So it says now the cylinder rolls without slipping only when it encounters a surface that has a minimum coefficient of 0.4. And so notice that minimum criteria, scenario C is 0.5, it's above the minimum. So it's good, it's non-slip. But scenario B was below the minimum. And so this is going to be where you have the kinetic friction. You're not going to grip the whole time. Maybe you grip to rotate some, but it's not that perfect scenario where it's a full grip, okay? Rank the scenarios. Now y'all are going to rank them at later point. Let's draw a diagram for each. Let's do the energy statement for each, okay? And so A, I'm going to try and color coded this. A, now we just care about it when it's on the ramp. All of them are going to start the same on the horizontal surface. So we're just looking at bottom of the ramp to top of the ramp. Okay, and so as it goes up, remember it had a clockwise angular velocity to start. So we gave it a spin to start. When it's on the ramp, what forces are acting on it? Well, scenario A is frictionless, so no friction whatsoever at all. But we do have that center of mass. We've got our gravitational force. Notice our ramp is tilted the other way, so normal force is going to tilt the other way. But they're both going to pass through that axis of rotation. So how much torque does normal force do? Still 0. So torque normal, still 0. Gravity, still 0. And so if there's no friction, no applied, no other forces, what's going to be true about the rotation as it goes up the ramp? It continues to be what it is. Objects rotating with an initial angular velocity. If they experience no net torque, there's going to be no angular acceleration. Alpha would be 0, so changes to omega would be 0. Your energy statement, what would it be? Well, at the bottom, we have 1/2 I omega squared. And we do have linear velocity. At the top of the ramp is going to be where it, won't this thing still come to a split-second linear stop? I mean, linear forces are still, gravity's still trying to pull it down the ramp. And so it's going to come to a split-second stop. So I'm going to show this, but then I'm going to zero it out. Okay? I'm going to zero it out. It does come to a linear stop. And now it has height. And so we have mgh, but there's no changes to the rotation. And so 1/2 I omega final squared, but note to self, these are going to be the same. There's no changes. And so what's the only energy converting? Linear kinetic converts to potential. Isn't that just like the box sliding up a frictionless ramp? Well, the picture, we're going to assume that all the initial conditions are the same. So we're going to start with spin. We're going to start. So it was given an initial push with an initial spin. Okay. All right. So that's A. Let's take a look at B. B has some friction, but again, it's not that optimal. So we're still going to have the same gravitational force, the same normal force, no torque, normal and gravity. Now we're going to have some friction, and it's going to slow us down, right? But sometimes it's gripping, so we just don't have that consistent. And so we started out with an initial clockwise, pay attention here, that friction is going to decrease the rotation sometimes, just not all the time. What direction does the torque of friction have to be to decrease this clockwise motion? It's got to be counter. So notice before I draw the force of friction, I'm considering what kind of torque friction needs to happen. Now trace it around. Let me use a different blue here to emphasize. Trace it around to the contact point. What direction is this friction to slow that rotation down? It's up the ramp. Now that's the same direction it was previously, but now it's in the forward direction, right? And so that force of friction, maybe sometimes it grips, maybe sometimes it slips, right? But yeah, this would have a lever arm. You would have a lever arm. You're going to have work done by friction linearly, and you're going to have work done by friction, torque done by friction to change the rotation. What would your energy statement be? Well, again, it all starts the same. We've got that initial rotation, 1/2 omega I squared. We've got the initial velocity that's the same as before. But this one is going to have heat loss. Heat loss. And so either subtract it from the left-hand side or show that some of your initial is going to turn into heat. Plus, we're still going to slow to a stop linear. I mean, what goes up must come down. And before you change direction, it's got to be a split-second stop. And so I'm still going to show 1/2 mv final squared, but I'll zero that out. Plus, we're still going to have some height. but we're also going to not totally be brought to a rotational stop. Friction is doing some torque to slow down the rotation, but maybe not all. And so we're going to have 1/2 I omega F squared. And note to self, these are going to be different. Okay. So that's B. C is our great non-slip scenario. So this is the one we're going to spend more time with, just like we did on the front. And so C, when it's on the ramp, what forces are acting on C? Well, we still got the good old gravity, good old normal, no torque for you, right? Hopefully we're catching on why these have no torque. And it does start with that angular initial velocity in the clockwise direction. It's going to move up the ramp. Friction is trying to non-slip. It's trying to create a torque to minimize that rotation. Because wouldn't you agree that if final velocity is 0 at the top, by the way, that was in the picture, then it non-slip, it has to equal omega final R. What's your final omega in this non-slip condition? 0. So the only force providing torque to minimize that rotation to 0 is who? Friction. What direction is friction going to act? What torque in order to minimize the clockwise direction? Counterclockwise is what we need from friction. And at the point of contact, it has to be what linear direction? Up the ramp, bigger than before, right? Static is bigger. This is our gripping friction. And it does have torque. It'd be equal to a lever arm of capital R, the radius of the disc. Okay. And it goes up, 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 up. Energy statement. Okay. In the beginning, we have that initial rotation, same as before. We have the initial kinetic energy equals, well, there's not any heat loss. We come to a split second stop. So I'm going to go in and show the split second stop. And then our rotation comes to a stop. And so what's left? Where does all this energy go? Exclusively to MGH. So that non-slip condition stops the rotation. Gravity, just like boxes on a ramp, is going to bring it to a split second linear stop. So all that energy goes all into MGH. And just because it's right there, the answer, I hope, is staring us in the face. First ranking, who goes the highest? C. C got all that initial energy in the form of MGH. It's going to go the highest. And you're like, what? But there's friction. Yeah, that gripping friction helps it go higher. It's an upward force on the object, right? So it's gripping to take it higher, you can think about. Or look at the energy. It gets all the initial energy converted to MGH. Who's going to go the least? No. A is going to be the least, because if you go back up, the rotation doesn't change. So it's just, it is what it is, and it ends what it is. And so that 1/2 mv squared does go into MGH, okay? But it has no grip at all at any points. And so again, B is going to be somewhere in between, okay? Mostly, okay. Okay, so I'll let y'all finish that one out. Let's do, there's 2 more pages with energy. I want to at least try, okay? And so it should feel the same after that, but there you go. Page 3. This one will go a little quicker. We've seen this picture before, but now we're going to take an energy point of view. And so we've got this sign, hanging sign or drawbridge, whatever you want to call it. when the rope is cut, determine the angular velocity when it is at the vertical. So maybe there's a wall and it's just before it hits the wall. Maybe there's not a wall and it's just hanging straight up and down. What's that angular velocity as it swings through? Now, eventually gravity is going to win. If it did swing back and forth, it would eventually stop at equilibrium, right? It's basically a long pendulum. We're not looking at 10 seconds later. We're looking at that first swing through the vertical. Good deal? Okay. And then later determine the linear speed for a point somewhere on the rod. And so the string is cut. So previously we looked at equilibrium with this one, but when the string is cut, cord is cut, no more equilibrium. So we're going to have a net torque equals I alpha. And so who's going to provide this net torque? There's no people standing on it. It's just the rod. And so we've got this center of mass, gravitational force, right? Fg or mg. It's got a lever arm, half the length. And so you could say mg times L over 2. And you would need to solve for angular acceleration before the angular velocity, right? Now, I started with torque. This is what we've done with this problem, but there's a problem. Fast forward a semisecond. So a semisecond later, where's the rod? Here's the hinge. Maybe it's right here. Okay. Now your center of mass is same. Mg is all the same. But where's your lever arm? Is it still L over 2? No, it's a vertical force. I need line of action. Your lever arm is here, but the lever arm is now less than L over 2. So torque is actually harder to use because it doesn't have a constant angular acceleration. And so alpha is not constant. The lever arm for gravity is always changing as it swings down, okay? And so we can't just say, oh, solve for alpha, solve for change in angular velocity over time. And so here is an example where energy is going to be more user-friendly because energy, you can look at just spots, okay? And so I'm going to switch gears. Let's take, so torque, not that it's not true, it's just harder, okay? And so we're going to take a look at the energy point of view. And so when it's at the top, just like it is in the picture, what kind of energy does our center of mass object have? What kind of energy? Potential energy. So we got potential energy, gravitational. In the end, again, when it swings through the vertical, then what kind of energy do we have? What kind of kinetic? It has, at all these points, it does have a tangent velocity, but it also has an omega, right? And so we've got some linear motion of the center of mass. We've got some angular rotational. And so final, we're going to have that KE translational and KE rotational. Now, if we call this the lowest point of your center of mass, then we can say no more potential at that spot. Good? Okay, so what would our energy statement read? And so we would have potential energy initially. It's going to convert into our kinetics. And we'll spend some time with that. And so mgh equals 1/2 mv squared plus 1/2 I omega squared. Everybody good? Okay, And it's not really like a non-slip like the ball on the ramp, but we'll assume that there's no friction in the hinge, because if there was, then it would probably not be consistent. So we'll say it's a frictionless hinge. I'll add that to our picture. So frictionless hinge. And so our energy is going to be conserved. And so I'm not going to put any losses in that statement. And so we can assume non-slip in our solving. And so non-slip, what can we plug in? Huh? So we're going to basically go back to the circular motion approach of that V equals omega R. We're still going to use that, but it's not like the ball on the ramp where it's gripping friction if we say the hinge is frictionless, right? But we're just saying that every moment you rotate, you're also translating, okay? And it's a smooth transition. And so what can we plug in? Right, we can say that K mR squared times V squared over R squared. R's cancel, R squared cancels, and it's going to feel very similar, right? Right. And so hopefully you see M's are going to cancel as well. So let me write what didn't cancel. And so GH equals 1/2 V squared, and that's the linear tangent speed, plus 1/2 KV squared. And so similar to before, what can we do? Well, I'm going to factor out the 1/2 V squared first and get 1 plus K. And then to solve for V squared, or 2GH divided by 1 plus K, whole thing square root. Okay. And so up above, they gave us what? Oh, I guess I'm solving for linear speed first. Okay. They gave us the mass, they gave us the length. Now mass canceled out. Length is going to help us use the height. And so we were looking at the center of mass. What height change would the center of mass undergo? Well, no, that was a different position. So it would have, yes. So it'd be half the length. Yeah, it's going to be half the length. So if height change is going to be half the length, they told us the length is 2 meters. And so our height change is going to be 1. K wasn't given. I forgot to put that in. So you don't have to memorize it. But the K for a rod that's attached on one end, 1/3. 1/3. And so this is actually going to be a tangent linear velocity of the center of mass. So it's okay. It's okay. We can work our way back. And so 2GH, I'll plug in a 10, I'll plug in the 1, and then 1 plus 1/3. And do that before you divide. So someone grab a calculator. And this is for the center of mass location. 3.87. Making sure that, yeah, okay. So this is the tangent linear speed of the center of mass when it's at the vertical. How could we find omega now? I guess we should have subbed in our non-slip equation in for V, but how can we find it now? V over R, right? And so 3.87, and the distance for that center of mass axis of rotation, kind of like a lever arm, would be at 1. And so omega is going to be 3.87, but not meters per second. It'd be radians per second, because you would divide meter per second by meter. Now, what about a point 1.5? So what about a point on the rod that's further from the axis of rotation? its linear velocity, is it still going to be the same? Angular for the center of mass is the same for angular to another point at 1.5 meters, right? They sweep the same angle, angular displacement in the same amount of time. So omega is the same, but they have different radii. They have different lever arms, distance from the axis of rotation. And so that now that we know omega, so omega is at 3.87, but V over R is now going to be 1.5. So it should be a greater tangent velocity. Let me know what you get. 5 point. Eight. Okay. And then this should come back to meters per second. Okay. You could do the same thing for the end of the rod. Just put a 2 meter there, right? And so just again, that connection that the further you are away from the axis of rotation, the greater the linear speed, but omega would remain the same. Good deal? Okay. And then page 4. So I think this is the last like energy application, at least the big, type of prompts. Pulleys, once again, pulleys. I thought we were done with pulleys. And so again, in the fall, we did forces exclusively. And then just last week or so, we did net torque of pulleys. Here, we're going to take an energy approach. And so at the end of the day, on the AP exam, if they gave you this pulley and they said, solve for this, solve for that, technically you have 2 approaches with rotation involved. Now, here's the hint. If they want velocities and speeds, maybe energy is your best friend, because kinetic energy, 1/2 mv squared. If they want acceleration, maybe net torques and forces are your friend, because that gives an acceleration result. At the end of the day, if you pick one approach and then you're like, oh man, I should have done the other, what connects linear and angular is that rotational kinematics, the non-slip equation, right? And so, don't totally erase if you're like, oh, I should have done the other way. Just use that connecting equation and rotational kinematics connection. Okay. And so similar to what we saw last time, again, now we're going to take an energy approach. M1 starts at rest with no friction on the table. And they give us some factors of, they say M1 is 1M, whatever M is. M2 is going to be 4M, and it's hanging off the edge. And it's going to have a height change. I'm going to assume it's going to fall to the floor. Okay. And that pulley has a mass of 2M, and it's non-slip, which means it is going to have gripping friction. Okay, so we got the grip, and you see that phrase and you go, oh yeah, I remember V equals omega R, A equals alpha R, displacement equals angular displacement R. Okay, non-slip, those scenarios, those are your key equations. And then they give us the shape constant. We'll keep it as a K for now, but later it'll be 1/2. And so for energy, one of the nice things about energy, you don't have to draw a force diagram. You just define your 0 meter mark and figure out who's translating, who's rotating, okay? And so later, when M2 has fallen a certain height, so H, what are the following? So this is a variable solve. Even though we have some numbers, it's not actual kilograms. So what's the VF? What's the final omega? KE total, rotational total, and then we'll make change. And so what would be our energy statement? And so again, forces, you got to do individual force statements and then put them together for a system. Here, we can just kind of look at initial at the very, very beginning, and then at the very, very end. And so initially, what kind of energy do we have if it starts from rest? Potential. Who has potential energy? M1, M2? Technically, doesn't the pulley have MGH? Now, let me ask you a question. We can write all this out. M1, we'll say, remains on the table. Is there going to be any change to the potential energy of M1? No, so I'm just going to note that, save us a little space. So it's there, but it's not going to change. It's not going to convert. And so the change in potential energy for block 1 is going to be 0. PE if you want. I try to use both. Same thing with the pulley. The pulley is not going to come off its hinge and fall. It's just going to rotate there. And so the change in potential, gravitational potential for the pulley is also 0. But M2 is the only one that's going to change potential and convert to other forms. Wouldn't you agree that as it falls down, the potential energy of block 2 decreases? And it's going to speed the whole system up. And so we're just going to take a look at the initial potential energy of block 2. It's non-slip, so no heat loss, right? No heat loss, so don't put work of friction anywhere. Yes, there's friction, but it's a gripping friction to rotate. And so where is all this potential energy going? Well, the split second before block 2 hits the ground, doesn't it have linear kinetic? And so if I keep with just that second block, it's going to have some linear kinetic energy, translational kinetic energy. Oh, hold on. I'm mixing up. Let's keep big ones. So KE2 translational. Isn't block 1 going to slide to the right? Linear motion, translational. And then what's the pulley going to do? It's going to rotate, right? So it'd be KE of the pulley, and it would be rotational. Now let's plug in the equations for each and see what happens. And so U, potential energy for block 2, is a 4 mgh, I'm going to say. We could go generic, or we can plug in the mass factors from the beginning. The translational kinetic energy for block 2 is going to be 1/2 of 4m times Vf squared. And then for block 1, y'all, forces is still true. Aren't they going to have the same linear acceleration? Aren't they going to have the same final velocity, m1 and m2? Okay. And so then I would have 1/2, and block 1 was 1m. Same Vf squared. Yeah, it's still the same motion, fluid forward motion, just like before, okay? So visually, if you were to watch this happen, you would see the same thing no matter if you took a force torque approach or an energy approach. And then the rotational of the pulley, we've got 1/2 I omega final squared. And hopefully you've guessed it, in all of these examples with non-slip, we're going to spend some time with that I and omega. So let's plug in some equations there. So 1/2 kmr squared, and that's the radius of the disk, whatever it is. Omega final, well, if you look at a tangent point on the outer perimeter, we get that Vf, linear velocity squared, over r squared. What do we notice happens? R squared cancels, leaving us with, oh, I forgot my factor. What factor of mass? Oops. 2. I need to put a 2 in here. Sorry. K2m. I was doing that for the others. I need to be consistent. And so 1/2 K2m. Okay, bringing down everybody else. And yes, y'all are already seeing, we're going to cancel mass. And then we'll spend some time with those coefficients, if you will. And so here's our statement after spending time with the non-slip pieces and inertia. And so yes, mass does cancel M, 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 M. And then we can actually, the mass factors are still there. And so we can simplify it. We get 4GH equals half of 4 is 2. And then we just have half. And then I'm also going to plug in our K value. They said it was 1/2. And so K is 1/2. And so what's half of 2? Yeah. Or just keep the half. And 2 plus, combine like terms here on the right. And so 2 plus half, 3 VF squared equals 4GH. We're trying to do all this to solve for VF. And so we would get what? 4GH over 3 and then square root. And don't worry, with variable problems, they didn't give us the height. And so even though we know gravity's 10, with variable problems, you don't have to plug in 9.8 or 10. If you did, you're showing your work, so the grader would count it. It's okay. But I'm going to keep this as my final answer. Okay? And so final answer, VF equals square root 4/3 GH, or 4GH over 3, same thing. Now, before we leave it, what if I had changed out? Well, I know they'll probably do this later. Yeah, never mind, I'll save it. I was going to make a change. We'll make our changes later. What about omega final? Right, V over R. And so square root of 4/3 GH over R. They didn't give us any factor of, did they? Just R. So that's your final answer. Nothing cancels or simplifies. So the square root's only in the numerator, by the way. Don't square root the whole thing. And then the next two questions, KE total, R, KE rotational. And by the way, we're kind of putting these in terms of the givens, okay? So you don't want to just say 1/2 mv squared generic, okay? And so total, this is KE rotational plus all of we've already written that statement, right? All the kinetic energies. But at the end of the day, didn't it equal potential energy in the very beginning? In our statement, it all began with our total kinetic energy. So if we look at this as KE total, doesn't it just equal MGH? 4 MGH, there we go. And so it equals that 4 MGH. H is, say one more time. So rotational, here we need to 1/2 I omega squared is where we would start. I omega squared, but even though they gave us the 1/2 MR squared, let's spend some time with that. So again, that same substitution should go quicker now. Oh, it was 2M, right? Yeah. Almost forgot it again. And then that V squared over R squared. And so we see R squared cancels out again. And K we know is that 1/2. But V was not given. And so what we're going to do here is plug in the V from above. Messy algebra. Let's do it one step at a time. And so I'm going to do the 1/2 of 2 ends up 1/2 M. And then the V, we got square root of 4/3 GH. No, I don't like that. Oh, we got to square it. Square it. Okay. I was like, no, I remember the answer being cleaner. Well, don't forget to square, Miss Earhart. V squared. And so what's going to happen to that square root? It goes away. And so we get 1/2 of M times 4/3 GH. Take care of your fractions. 1/2 of 4/3 would be 2/3 MGH. So notice it looks like it's in terms of MGH, your initial potential energy. Our total is 4. 2/3 goes into rotational. And so 2/3 of, could we do a percentage? So our initial is 4 MGH. Let's do a percentage. AP will have you do this randomly. And so what percentage goes into rotation? And so it would be your rotational kinetic energy divided by your total times 100. And so we have 2/3 MGH over 4 MGH. MGH as a variable cancels out. And so what would we get here? 2/3 times 1/4, or we'd get, yeah, I feel that's right. 2/12, 1/6 times 100, whatever it is, right? Whatever that is. Somebody tell me. 16. So 16% goes into rotational. It all started with 100% potential. Where does the other 84% go? Translational kinetic. Both of them are kinetic. There you go. Now, if you change some of the masses, like especially M2, if your hanging mass changes, for sure, you're going to have different values, right? It's the one driving it all. And so a little percentage breakdown. No percentage equation is on the formula chart, but occasionally I've seen them, you know, what percentage of heat is lost. You would find the heat value divided by your total, where it all started, times 100. Small over big times 100. Okay, to finish it out, and then maybe y'all can try some on that page too. This will wrap up energy. I feel good. I feel good. Hopefully you feel okay. I know it's day one with energy, but what if the pulley were replaced with the following? What would happen to the rotational kinetic energy? And we could also add in, you know, rotational and translational. So what if we have another disc on the pulley and it has a higher mass? Okay, and so if we look at the rotational piece, if the pulley mass goes up, inertia goes up, rotational does what? It's harder to rotate, so it would take more energy to rotate the disc. And so a higher mass of pulley would mean a higher inertia, a greater kinetic energy rotational, and just note to self, it would mean it's harder to rotate. And if the question had said translational, that 4 MGH stays the same, but now I got to have more in rotational. How much is left for the translational motion? Less. Okay, what if we used another disc, same mass, same original mass, but now it has a larger radius? Still assuming non-slip. Well, they're just asking what happens to the rotational kinetic energy. Just for this whole term. Yeah, it cancels. It doesn't change. So yeah, rotational, non-slip, again, has to be the, so still assuming non-slip on all this. What do we change? A larger radius, but R squared cancels in the KE rotational. And so it'd be same. And we'd have the same translational. Good there. And then we've got a hollow ring of same mass and same radius. And so hollow, conceptually, you don't need to know the number, but conceptually, what's happening here? it would mean a higher constant, a higher inertia, harder to rotate. And so what would happen to your rotational kinetic energy? It would increase. What would happen to translational? It would decrease. Okay. Now, a hollow ring, true story, they'd probably have to have some kind of rods and put it on a spindle. You can't, rotate about the center when nothing goes through the center to keep you in place. Okay. But hollow ring overall. Good deal? Okay. So just a little bit of time. See if you can go answer some of the rankings for page 2. Okay. And I think, I'll double check, but I think Key's already on Canvas for you to check those answers. Next class, we'll get into angular momentum, and we'll keep doing energy because those collisions, elastic, inelastic, all that stuff, it's coming back. Okay. Okay.